Hi everyone, we are back and we are going to do our Pset 1 solution video. So read the following article and fill out the materials tetrahedron. So I'm going to do my best to draw our materials, although I'm awful. Here we go. So we have structure, we have properties, we have processes, and we have processes, and we have performance. So let's go ahead and let's look at this article here. Actually, can I? PNAS, VFW. Let's go ahead. I believe this will be the same. Yep, there it is. All right. So if you all have read this article, and it's looking at the shear-induced folding of von Willebrand factor. So basically, what's happening here, if we can break down this process, we have a protein that at low shear, von Willebrand factor is in this globular form. So it's like a ball. When your body is cut and there's high shear rates, this protein unfolds and it exposes binding sites that grab blood cells and cause your body to clot. So if you have a defect in this protein, von Willebrand factor, VWF, then you're in a little bit of you're in big trouble because your body can't clot. So if we look at kind of just the normal process where we don't have basically defects in von Willebrand factor, so what happens? So we have structure. So our structure first at low shear rates is this globular form. Something happens where we're cut and we basically undergo a process where our shear rate increases. So by the shear rate increasing, we change the structure. So now our protein, which was previously not able to grab red blood cells and clot, now exposes those binding sites, becomes elongated, and now we've changed the properties because now when we're exposed, we have these binding sites that are sticky. It can now bind, the adhesion increases, it binds to red blood cells, and then our clotting performance increases dramatically. So that's it. That's what we're looking at here. All right. Now, let's go ahead. True or false statements. Ionic bonding exhibits delocalized electrons. No, that is not true. That is metallic. So metallic bonds. An electronegativity difference of 2.1 classified as polar covalent. No, that would be ionic. And our cutoff is about 1.7 again, at least for this class. To investigate a millimeter length scales, I need to use a wavelength on the order of angstroms. No, I would need to use a wavelength on the order of millimeters. Because if I want to investigate that structure, I need to make sure that my wavelength is commensurable or about the same size as the distance between the spacing or the length scales I'm looking for. H bonding is intermolecular interaction. Nope, it is inter, and it has energy on the order of a kT or less than a kT. Perfect constructive interference is the only requirement for Bragg diffraction. Nope, we need to have obstacles, a regular space series of obstacles. We need to have a wavelength on this, and we need constructive interference. We need 3 criteria. Excellent. Metallic bonds are intramolecular interactions. Cl it's an anion. It will be an anion with a 1- charge. Ionic bonds can be broken at room temperature. No, only intermolecular interactions can be broken by kT, which is thermal energy. Intermolecular interactions can be broken yes, that is true. Yep, that is one of our only true ones. Van der Waals interaction is classified as intermolecular with energies, again, less than a kT or on the order of kT. Excellent. So what type of bonding will be exhibited by, MO, that is going to be metallic. They will not spontaneously reform at temperature, and then these are delocalized electrons. Let's look at BCl3. So I'm going to pull up our periodic table. So we need to look at electronegativities. So I need to look, let's look at, for example, we need to find electronegativities. It's going to be the second, basically this is the second number there. So for boron, I think they're both going to be on the other side. Yes. So boron, we have 2.04. And for chlorine, we have 3.16. So boron is 2.04. Boron 2.04, and this is 3.16. So let's go ahead. Let's calculate that difference. And if we look at our, let's see, 2.04 boron, and if we look at our, actually, we're going to look at our, let's look at this week. We're going to go to our LibreText because I always have an issue. What's our, what is our differentiating between those bonds? Greater than 1.7. Okay, so we know that this is not greater than 1.7, so it's going to be some type of basically polar covalent, so they are going to be shared in some manner. Polar covalent. They can't be broken and reform at room temperature. CH4, this would be actually, this is basically kind of like a methyl group, but this will be basically pure, actually, let's look at our difference between CH4, what type of bonding, where's our periodic table? Periodic table, where are you? Where is it? We just saw. Oh, it's probably in our here. There we go. So C 2.55, and then 2.55, 2.22. Yeah, that's basically going to be almost, that's going to be covalent, pure covalent. And then so that would be shared, can't be rebroken at room temperature. Polycarbonate is PC. So let's look at polycarbonate structure, chemical structure. So polycarbonate has a backbone that looks like this, and it repeats. So here we can see we have oxygens, we have basically double bonded COs. So we're going to have actually several. So we have along the backbone covalent interactions. We also have steric interactions because of those big bulky groups. We're going to have some type of polar / dipole interactions because of the oxygens. They're going to want to pull electrons. They're very electronegative. So you're going to have basically a combination of intra and intermolecular interactions there. Fantastic. All right. In an MgLC2 crystal, what's the cation? It'd be Mg, and that's going to be 2+, and Cl will be -1. Again, this will give up 2 electrons. This will gain an electron. Zr2O5, so Zr will be basically a +5. O will be a -2. Same thing there. K will be +1. Cl will be -1. Finally, we are going to use, and actually I used this previously. I'm going to evaluate, because again, I don't want any crosstalk. So I'm going to quit my kernel. I'm going to delete all this. We are going to look at our Lennard-Jones potential. So our ULJ is going to be equal to 4 times eps. I'm just going to call it epsilon times sig divided by r to the 12 minus sig divided by r to the 6. So that's our Lennard-Jones potential. We are told that, excuse me. We're trying to approximate it as vanadium. The energy at equilibrium is -2 eV. What are the values of, okay, so we're trying to approximate it here. Okay, so we know if I take the derivative of ULJ with respect to R, excuse me, this will give me, because we know our Lennard-Jones potential looks something like this, and this gives me, when I set the derivative equal to 0, and we know that our force is equal to, actually let's define that right now. our force equals minus derivative of ULJ with respect to R. So that's our force as well. But when I set the derivative of the function, it'll give me this value here, this R, and that's going to be equal to our equilibrium distance. If we're looking to approximate this as vanadium, which is what the project statement tells us, so I need to look at vanadium and then look at the metallic. Vanadium is a metal. It has a metallic radius of 1.36 angstroms. So I'm going to say, VD radius equals 1.36 times 10 to the minus 10, because that's angstroms. So we basically have here, if we look at these solutions, we can't have a negative radii, and these are all imaginary numbers. You can actually do some tricks, like say, but we're not going to go ahead and do that. So basically, we need to have this and solve. When does this equal 2 times VDR? We'll solve it for sigma. So this is our sigma. So we've solved that because we're just setting that equal to one another, because we're basically asking, what is the, we know it's going to equal this value if we're trying to approximate vanadium. Fantastic. So that's our sig. We can now look at our force. So now our only unknown is this, but we're given additional information in this problem. This is a fun problem. That energy at equilibrium is minus 2 electron volts. So at equilibrium is basically saying, okay, well, we are going to say ULJ, and then we're just going to say the energy. So ULJ slash dot R goes to 2 times V, what is it? Call it Vand? What do we call that variable? VDR. VDR. So we're going to solve, when does this equal, and we'll just keep it minus 2. We'll solve. So our epsilon, eps is equal to 2. There we go. We found that value. What is the value of the force? So force slash dot R goes to 3.5 times 10 to the minus 10. We've got that value here. What is the value of force at 2 angstroms? We can put that right here. 2. You can see kind of the change in the sign. What about the potential energy? So instead of force, we would just say, I would just do force. I'd just say ULJ. And then I'd put ULJ right here. You can see the different values. Cool. And you can put that in the context of the potential energies there. Fantastic. So that is it. That's Pset 1 Solutions. So we'll see you in the next video. Thanks. Bye.